Okay, so in a moment here, I'm going to make sure to hand back your quizzes from last time. We're going to talk about the last little bit of rotational motion that we have to go. That's angular momentum. We've basically, in the last 2 weeks, we've recovered the entire semester, with the exception of momentum. So we're going to talk about angular momentum here. Um, I got a couple of demonstrations for you, and then you'll have some work time. Uh, a couple things about what's coming up. Um, again, presentations start April 7th, but I want you to think about presentations as being due before break. There's something I'm collecting by then, but I just don't want you to have to think about it over break. Um, just a reminder, because it's been a while since I said this, remember the format of the presentation are that we're going to have like 5 or 6 like stations around the room, and you're going to give your presentation. You're going to give your presentation to like 3 or 4 people at a time, but then you're going to give your presentation 6 times. So it's like a small group presentation, and you're going to give it multiple times, and then everyone's going to rotate through your station, and I'll rotate through as well. So that's how that's going to work. So just when you're thinking about it, it's not for the whole class presentation. You got your laptop at your table, you present to the small group. Does anybody have any questions about presentations? It's been a while since we talked about it. All right. Test day is going to be last day before break. So next Thursday is test day for this, and that's when the rest of the syllabus is due. I understand, by the way. So I try to go in like the due dates that I post on the syllabus. I try to update the grades every one of those times, because like it keeps me and I think you in like aware of where we're at. The zeros are not real zeros until testing, right? I put zeros in, then you know like it's sort of a reminder you have to do it. But remember, the the real due date is test day. There's no penalty if anything gets turned in before test day. Okay. For the sake of time, will you guys please remind me after, because I'm going to do the notes first, but will you remind me when we get to work time, make sure I hand back to you? Please don't forget that. I want to make sure you have that back. Anybody have any questions they want to go over on anything before I do the notes? Go ahead, Chris. Stay at 52? Okay. Yeah, good question. Good one. All right. So a bowling ball of mass 7.25 kilograms and radius 10.8 centimeters rolls down without slipping a lane at a speed of 3.10 meters per second. And it wants to know my kinetic energy. Now, the kinetic energy, though, there are 2 types. Because if you're rolling, you're translating and you're rotating, right? So 1/2 mv squared plus 1/2 iota omega squared. And if you recall, when we did the conservation of energy problem the last time, we used the equation V equals R omega to say that omega is V over R. So instead of omega, I'm going to write V squared over R squared. And I think since this is a ball, right? You can plug in 2/5 mr squared for iota, and that's how you do that. Is that all right? Anything else? All right, so let's go ahead and continue our notes then. So again, last set of notes for rotational motion, and we're going to label this momentum. And just like we've been doing, we'll make our chart. In theory, angular momentum is a very simple concept, but it has some really interesting and surprising effects. So we're going to start with, again, the idea of translational momentum. So what we've talked about it so far is translational momentum P, which we defined as mv, right? And even though we have not been very careful about putting our vector hats on things, I want to be clear on this, that when we talk about this, momentum is a vector, velocity is a vector. So angular momentum is going to have the symbol L. It's really weird because linear momentum is P, angular momentum is L. Also, every other angular quantity has a Greek letter, but angular momentum is L. I don't know why, but that's what it is. Anyone want to guess what the equation is, given what's parallel to this? Go ahead, Malachi. Yep. So parallel to mass is iota, parallel to velocity is omega. And it turns out, let me think about this for a second. Make sure I'm saying this right. Yeah. There's a comment, there's a connection here that we won't use very often. I don't even think I put it on the equation sheet, but it turns out that angular momentum is the radius times linear momentum. At least when I'm talking about a particle. Okay, there are a couple things we've got to be careful about with angular momentum, though, because I define this thing as a vector, but we've got to think about how we're going to talk about the vector, because things that are going in circles are kind of a pain to deal with. Let me get my bicycle to show you. It's kind of a pain to talk about the direction of a rotation, because, well, if I look at a point on this wheel, right, it starts going this way and now it's going that way, right? So it's kind of, there are points on the wheel traveling in every which direction, right? And so we need a way to deal with, to be able to call momentum a vector. And so we have a convention that we use. The convention that we use is called the right-hand rule. So anybody come across right-hand rule maybe in, it's possible in an engineering class you might talk about. Anyone heard of the right hand rule? Okay, that's right. So the right hand rule, so the idea is if you've got, so I'm going to draw a disc that's rotating. I'm going to say that it's rotating this way. If it's rotating that way, the right hand rule says if you take your right hand and you make your, now I can't do it on this screen, but if you take your right hand and you make your fingers curl in the direction of motion, right, then your thumb points in the direction of the vector. I'm going to do this for the people who are watching at home maybe later, right? So the idea is if I take my finger and if it's rotating this way, right, my fingers, if I make my fingers, my right hand, it has to be your right hand. You make your fingers curl in the direction that you're spinning. My thumb points up, which means in this case, by convention, we're going to say that the angular momentum vector points up. You can actually do this. This is actually a convention that we use with, or that if you go into AP Physics, you'll use this with all of these concepts. But angular momentum is really the only place we're going to talk about it here because it just makes it a lot easier to deal with. Yeah.
Yeah, why there's like those boys that you like spin them really fast and then launch up into the sky?
Yeah, well, kind of. So those are, again, this is a convention. It's a man-made convention. We could have made this left-handed, right? But there is a like, because we define these things as right-handed, we tend to build things that way, right? So if you think about a screw, if you've ever done righty-tighty, lefty-loosey with a screw, right? So think about if I was turning a screw into the wall here, and I did righty-tighty, right? Righty-tighty, my fingers curl this way, it goes into the wall, right? That's because generally screws are manufactured right-handed. You can get a left-handed screw. There's nothing physically, like physics doesn't require that you use a right-hand rule, but it's just a convention that we use. And so, I mean, wrenches, most wrenches, most screws, most things, right? If you righty-tighty, lefty-loosey, if you go right, you curl, it's going to go in, right? Lefty-loosey, if you go out with your right hand, it's going to come out. So you might hear about, there are sometimes, like, if you've got a motor that is usually going counterclockwise, right? You can't put a right-handed screw on it because it's going to work itself off. So they manufacture left-handed screws that do the opposite. But by convention, most of the time, most screws are right-handed, and they follow this pattern. Right? Okay. So this is just, like I said, this is just a bookkeeping method, because if I were really to talk about the actual vector, the way these things are moving, some things are moving this way, the things on the back are moving that way, right? But we're going to use this convention, this right-handed convention. And just to kind of test this out for ourselves, if I do something like this and I make it go left, so again, you have to use right-handed. If you make it go left and you curl your fingers, your thumb points down. So this would be a case of a downward angular momentum. All right. Because you can deal with angular momentum, we can do things like conserve angular momentum. So just like before, we could take, we could say that sigma p equals sigma p prime. We can do the same with angular momentum. Sigma L equals sigma L prime. Instead of doing problems with that to begin with, I think it's more useful to see applications. Now, what I want to do real quick is I want to hand out to you a short reading, and we're gonna do this reading, and then we're gonna discuss this to make sense out of this. All right, when you get this, I'd like you to go ahead and start. Go ahead and start. The first page is the page that says 8.8 on it. So I just want you to take a minute. Actually, I'm going to have you read both pages to yourself to begin with, and then we're going to discuss it here in a second. Okay, what I'd like you to do then is I want to focus for a second on this diagram, figure 8.52. I want you to start by just explaining to your partner what is happening there. Why is this an example of conservation of angular momentum? All right. I think I'm gonna pick someone for my cards for this. Martin, you want to explain this to us?
Yeah, so in the first picture, his rotational inertia is kind of like spread out. The weights are right here. So in order to compensate for that, he's going to go slow. But in the second picture, when he pulls them in, the rotational inertia is a lot closer together and compact. But because sigma L equals sigma L prime, then he has to go faster to complete the system.
Right, yeah, and this is kind of what this is saying, right? And by the way, the author here is using the term rotational inertia. We've used the term moment of inertia, right? Same thing. But the idea is mr squared, you've got your m at a big R, so big iota. You've got your m at a small r, you've got a small iota, right? So the omega has to be inversely proportional. I want to see if we can get this to work, and we're going to see if we can get this to work without me killing myself. So let's see. I have no skating experience or anything. I'm not very graceful at this, but I think we can make it work. So if I start spinning, and then I bring them in, whoo, right? Okay, so I start myself with some sort of angular momentum, right? Maybe. Okay, just a second. Here we go. Angular momentum. One more time. We'll try again. Angular momentum. No. Went well the first time. We can do this. Yeah, I'm going to call myself good. My turntable see better days. All right, try one more time. You got a big iota out here, small iota in here. So if I can get a big iota, small omega, now I have a big omega. All right, the only thing I'm changing is where my mass is located. Right? So that's the idea there of angular momentum. Okay. Next question I got. How might a figure skater make use of this? Try what you think. All right, Grace, you want to try this? Uh-huh. Yeah, they usually kind of start again, I'm not gonna be able to do this big, but they're gonna start something like this, right? And when they get spinning, now they can do this, right? And all of a sudden they've taken their iota in. I can say less iota and go bigger. They can go faster. Remind me in after we're done with this, I'll show you a video of that. See that. All right. What else do I have here? Okay, this one's really interesting. So it talks about the cat on the back. But this takes a little bit of digging into it to really understand it. So you've heard the idea of a cat always lands. It's not a physical law, but a cat can take advantage of the laws of physics to try and make this happen. All right. So I want you to take a look at what it says about that and see if you can like summarize how is a cat able to land on its feet. So see if you can summarize that for your partner. All right. Sohaib, what are you thinking about this? Well, so let me ask you this: though, if the cat is falling like this, so this is his feet are up, right? If the cat is falling like this, how is he gonna? If you're falling like this, how do you turn yourself around? Logan, what do you think?
It's like the first either whole body and then like rotating the entire spine.
And the key with the spine is what to do it. Yeah, so let's think about this. Angularly, so translationally, there's momentum to the cat fall. Angularly, if the cat falls back down, right? Angularly, how much momentum does he have? None, zero, right? He's got zero momentum. He's got to keep zero momentum. How can you keep zero momentum but get your legs around? Well, if you do this, right? If you do one of these things, right? If you can twist so that your front legs can go forward and your hind legs go back, right? One side of the cat has an angular momentum pointing this way. The other side of the cat has an angular momentum pointing that way, right? They can cancel each other out, right? So that's what's happening to begin with, right? But then what happens is you do this, you got your back legs are pointing down now, right? Why are you not going to land twisted up? Here, you guys understand. So the idea is this hand is kind of supposed to be like this is his head, right? These are his back legs and his tail. Okay. So if I do this and I can get my back legs so that they're aimed correctly, it seems like I'm going to land twisted up, right? How do we address it? We've got to maintain zero momentum. So in other words, we've got to untwist. But if I untwist, why don't I just go back to this? So think about this. Think about the skater, right? What is different between when the cat wants to untwist? What do you need to do? What do you need to do with his legs? Which legs need to extend? The legs that need to extend are the legs that are already correct, right? They're already pointing down. Front legs, in this case, need to come in, right? Because now you have big iota in the back, small iota in the front, right? So the front can twist faster than the back, right? So there's kind of two things that happen for a cat to correct themselves. Yeah, actually, I think I have to do this. Give me 1 second. It's a lot easier to see in the video. What'd you say? What'd you say, Solis? Oops. Let me see. I think I saved a video last year, although now oh, come on now. Uh, all right. Let me,
Hey, it's me, Destin. Welcome back to Smarter Every Day. So you've probably observed that cats almost always land on their feet. Today's question is why? Like most simple questions, there's a very complex answer. For instance, let me reword this question. How does a cat go from feet up to feet down in a falling reference frame without violating the conservation of angular momentum? Now, I've studied free-falling bodies, my own in fact, in several different environments, and once I get my angular rotation started in one direction, I can't stop it. Today, we're going to use a high-speed camera. We're not going to use Allie because this is my daughter's cat. I don't want to hurt it. We're going to use a stunt cat. Let me introduce you to Gigi, the stunt cat. I'll just flip the video vertical and then motion track the cat. It's just going to take a lot more effort in post. We're going to try to do it in a way that doesn't make anybody mad. That's pretty hard to do. You got to drop a cat. Ready, Gigi? Good. Checking out the high-speed data there, Gigi?
okay, so going in separate directions. Now,
Okay, the first thing a cat does when it's falling is try to figure out which way is up. It does this either with the gyro in the ear or with its eyes. 3, 2. Ready to talk cat physics? All right, so check out this footage I captured with the Phantom Miro while Gigi goes to get a drink of water. So here's what's interesting about this to me. If you'll notice at the beginning of the drop, the cat is not rotating. Halfway through the drop, the cat is rotating, and then at the very end, Gigi somehow stops rotating. Newton's first law says that an object at rest will stay at rest unless acted on by an external force. I see no external forces on this cat. So what's happening here? It's not making sense to me. Okay, so in order to really get the right data, we're gonna have to drop her 90 degrees out of phase. Ready, girl? This time, watch her tail. 3, 2, 1.
okay, tail is going counterclockwise, right? Feet are going clockwise. And then we can extend legs to increase mobility.
Okay, so you think you figured it out? Check this out. You probably noticed that when the cat was falling, her tail was rotating in the direction opposite of where her body was rotating. What's interesting about that is that that's not how it works. In fact, even bobtail cats can do this. It's called the cat riding reflex. I'll prove it to you. I came across some video from the 60s when the Air Force was researching microgravity for future astronauts. Turns out they took some cats up on parabolic flights. He tries to rotate his tail to flip over, but it doesn't work. He just ends up nutating wildly. Then he does something interesting. He takes his back and he bends it. And when he bends his back and then creates motion, something interesting happens. Ah, now we're getting somewhere. So let me show you one more cat flip with the Miro and we'll figure this out.
Here goes.
Okay, the arched back ends up being pretty important. What he does is he divides his body up into two separate rotational axes that are tilted from one another. When he's released, he pulls his front paws in and does the ice skater trick. He decreases his moment of inertia in the front so he can spin fast up there. But in the back, he pushes his legs away from him, increasing his moment of inertia. So a really large twist in the front equals a really small twist in the back in the opposite direction, and the torques equal out. So as soon as he gets his front paws in under him, all he has to do is extend those legs back out to increase that moment of inertia and stop the front twist, and extend his back legs along that rear axis. That allows him to twist those around really fast, and then all he has to do is pull them back in under his body and then extend all four legs and brace for impact.
All right, back leg means low iota, right? So, yeah.
So thank you for your attention. I hope you learned something pretty cool about cats. If you don't mind, woo! okay, I'm done. If you would, go check out your other cat videos after trying to catch Gigi. Whew, a little too rowdy. If you'd like to, click Gigi the cat to subscribe.
All right. So anyway, all right. So you gotta have opposite rotations to maintain your zero momentum, right? So you can manipulate your iota in the front and the back to make one side go faster. Any questions? I need to save this link because that was pretty good. All right. No. Oops. All right, let's talk about the next one here. Let's see here. I like this question. I think this is a good thinking question. You know how a helicopter, it's got the big rotor on the top. It's also got the small rotor in the back. Okay, think about conservation angular momentum. Why do you need that small back propeller? How far do we think about that? Anybody want to try this one? How do you have to have that small back propeller? Go ahead, Becky. Well, it definitely does. So it serves more than one purpose. There is it does need a purpose to like steer you. Yes, that is important. Like, and it turns out that the way a helicopter actually goes forward is it tilts itself so that it's aside from having lifted up on the forward component. So it does play a role in steering, but it plays an even more fundamental role. Yeah.
So if you probably just have the back propeller,
Yep.
would while the main propeller is rotating, would the helicopter itself rotate in the opposite direction?
Yeah.
And so, like if the blade of the main propeller running clockwise, so put it with the back propeller on the left side.
Or yeah, so that it's pushing against it, right? The idea is, and we got to be a little bit careful. It's not necessarily that if you like started a helicopter from all eternity as having a clockwise rotation, and you set it at rest, like it would maintain angular momentum. You wouldn't need that. But every time that your angular momentum changes, right? Every time the angular momentum of the top rotor changes, what's going to happen? The rest of the helicopter is going to go against whatever that change is, right? So you have to have a way to not conserve angular momentum, right? Remember, angular momentum is conserved unless you have an outside torque. So you got to provide some sort of outside torque to go against it. If you ever watch any of the war movies, right, when a helicopter gets shot down, right, if the back propeller gets shot off, right, what's it going to do? Right, the rotor is going this way. The rest of the helicopter has to cancel out that rotation, and so it kind of rotates out. So the back propeller kind of keeps it. It provides sort of like counterbalance to what the conservation of angular momentum would make the whole body of the helicopter want to do. All right. This says if we're doing we're not doing this. So here's the other really cool thing to do. So what I want to do is I want to do another angular momentum. I want to give bicycle wheel here an upward angular momentum. Which way should I do? Direction 1, direction 2. Think about which way up. Direction 1, direction 2. What do you think it is? 1, right? Everyone see this? If I curl my finger like this, if I want an upward angular momentum, I got to go like this. What I'm going to do is I'm going to give my wheel an upward angular momentum. Then I'm going to stand on the turntable. And I'm going to do this. See that? All right, so at the end, let me see if I can get it a little bit better. Upward angular momentum, I flip it over. I appear to start turning, right? So one of those things, and in a minute I'll let people try this. This is one of the things you're gonna have to feel it to actually believe what's happening here. But I want you to take a moment to explain what's happening here. Why is it that I give this thing an upward angular momentum? Why is it that if I flip it over, I start spinning? So, tell your partner what you think. All right. Andrew, what do you think about this? Why would I turn why do I start turning? Not sure. Fair enough. Brady was.
So like as you're turning it,
Yeah.
part of the motion is like also going that way, so it just kind of turns you when you flip it.
Part of the motion, when you say a little bit more about that part of the motion.
So when you're turning it and you're going like that,
Yeah.
when you're turning it, part of the motion is also going that way, like as you're like.
Okay. Yeah. So the idea, so this thing going like this, right? So yeah. So when you say part of the motion, you're kind of talking about like this thing is doing this, right? And all of a sudden it's not doing the opposite, right? You can think about this to keep it easier to think about, right? I want to think about it in terms of the angular momentum vector we defined, right? What's happening is I'm starting with upward angular momentum. When I do this, my upward angular momentum all of a sudden becomes downward angular momentum, right? But angular momentum has to change, or has to stay the same. It can't change, right? So if I have upward angular momentum, right now I just have upward angular momentum. If all of a sudden the wheel has downward angular momentum, what do I have to have? I have to have upward. Not only that, but how much upward angular momentum do I have to have? Think about it. It's not the same as the wheel, because if it were the same as the wheel, I'd cancel out the 0. I need to get up angular momentum. So I would have to have twice the angular momentum of this, right? So let's think about it again. Maybe this would be helpful to draw out for a second. So you imagine what's happening here, right? So I'm standing, I'm gonna do it. This is gonna be a very poor drawing, but it'll get the point across. So here's a wheel that's going this way. So it's gonna have an upward angular momentum. And I'm gonna be standing here. And this turntable is gonna have no angular momentum, right? If all of a sudden I flip this thing, so that I have downward angular momentum. In other words, you could say that my angular momentum here was L. My angular momentum here is going to be negative L, right? If my angular momentum here is negative L, what's got to happen? I need momentum before to be equal to the momentum after. The only way to make the momentum after the same is if I have 2L up, right? because negative L plus 2L is equal to L, right? Because I need momentum to be conserved. If I take an upward momentum and flip it to downward momentum, right, then the result is you get twice as much upward momentum for you. Now this was one of those things where if you actually see it done on someone else, it really is interesting to like feel for yourself, because this is not anything that I'm doing to like make myself rotate. It's all coming from the wheel. So I wanted to give anyone who wanted an opportunity to come up here and try this. I want to try this, but so go ahead and hold this first, and then I'll get it spinning. Ready? All right, and then you can stand on it. And then if you just flip it back and forth, you can kind of feel it like fight against you. Anybody else want to try this? It's one of those things you really have